In September 2020, the chief designer of China's deep-sea submersible Fendouzhe stood before a press conference and said something that most of the world did not notice. He said the bottom of the Mariana Trench was full of resources. He said they were going to make a treasure map. The world moved on. There were other headlines. There were other things to worry about. But beneath 11,000 meters of water, in the coldest, darkest, most isolated place on the surface of this planet, something was waiting. It had been waiting for 10,000 years. It had been stable for 10,000 years. It would not wait forever. The Mariana Trench is not just the deepest place on Earth. It is a pressure vessel, a geological cold storage unit, and locked inside the sediment of its floor, beneath the gray silt, beneath the ancient rock, beneath billions of years of accumulated marine snow, is one of the largest deposits of methane hydrate on the planet. Methane hydrate. Ice that burns. It exists only under specific conditions: extreme cold, extreme pressure, and the precise chemical balance of deep-sea sediment undisturbed by human activity. Change any one of those conditions, even slightly, and the hydrate destabilizes. The methane inside it, compressed and frozen for millennia, is released. And methane is 80 times more potent as a greenhouse gas than carbon dioxide, not 10 times, not 20 times, 80 times. In July 2025, a Chinese research vessel discovered the deepest living ecosystem ever recorded, a colony of worms and mollusks thriving at 9,533 meters depth, surviving entirely on methane seeping naturally through the seafloor. The discovery made headlines for 3 days. What the headlines did not say was this: the methane those creatures were eating was the same methane that, in hydrate form, exists in quantities large enough, if released, to accelerate global warming by a degree that our climate models are not fully prepared to calculate. And 3 months after that discovery, China's deep-sea mining program submitted its updated operational plan to the International Seabed Authority. The drill sites were 40 kilometers from the colony. This is the story of what happens next. This is the story of what happens if the drill goes in. What if China accidentally triggers the methane bomb under the Mariana Trench? Before you go down, you need to understand what is actually down there. Most people, when they think of the deep sea floor, imagine mud, gray, featureless, lifeless mud. The reality is more complicated and more dangerous. The sediment of the Mariana Trench floor is a layered archive. Millions of years of accumulated material, each layer a record of the ocean above it. Marine snow, compressed, organic material, fossilized. And within certain layers, under specific pressure and temperature conditions, something remarkable happens to the methane produced by the decomposition of organic matter. It freezes, but not into regular ice. Methane hydrate, also called methane clathrate, is a crystalline structure in which methane molecules are trapped inside a cage of water molecules. It looks like dirty ice. It exists at the intersection of high pressure and low temperature, exactly the conditions found in deep-sea sediment worldwide, including the Mariana Trench. The global methane hydrate deposits on the ocean floor contain more carbon than all the world's coal, oil, and natural gas reserves combined. Let that settle for a moment. More than all the fossil fuels we have already burned, more than everything we have already extracted from the ground in 200 years of industrial civilization, sitting frozen in the sediment of the deep ocean, stable for now. The stability of methane hydrate depends on two things: pressure and temperature. Reduce the pressure or raise the temperature and the hydrate dissociates. The crystalline cage collapses. The methane inside is released as gas. Deep sea mining changes both. When a mining machine moves across the seafloor, even carefully, even slowly, it disturbs the sediment. It creates pressure differentials. It generates mechanical heat. It stirs the carefully layered archive of millions of years into a turbidity cloud that rises through the water column like smoke from a fire. And in the sediment it disturbs, the hydrate begins to destabilize. Not all at once, not in an explosion, slowly, quietly, invisibly, the way Venus's ocean evaporated. This is where the what if becomes personal. You are a marine scientist attached to an independent monitoring mission. Your organization has been granted observation rights, a small habitat bolted to the seafloor at 8,200 meters depth, positioned 30 kilometers from the approved Chinese mining zone. Your mission is to observe, to record, to document whatever happens to the ecosystem in the vicinity of the drilling operation. You are not supposed to intervene. You are not supposed to make contact with the mining vessels above. You are a witness, a camera, a scientific instrument with a heartbeat. The habitat is smaller than the one in HADAL's first mission. 2 rooms, 1 bunk, equipment filling every surface that isn't occupied by the person sleeping in it. You have been here for 3 weeks. Outside your reinforced quartz window, the familiar darkness of the HADAL zone, the marine snow drifting down from 11 kilometers of water above, the occasional pale amphipod scuttling across the silt, the faint bioluminescent flicker of something in the mid-distance that your cameras cannot quite resolve, normal, quiet, ancient. Then, on the morning of day 22, your sediment sensors register something. A vibration, not an earthquake. You know what those feel like, and this is different. Slower, more rhythmic, more mechanical. The drill has reached its target depth. The mining operation has begun. It starts with the marine snow. You notice it on day 24, 2 days after the vibration began. The snow is different, still falling, still constant, but its composition has changed. Your water sampling system is pulling in particles that are not organic. Fine mineral sediment, disturbed from the seafloor by the turbidity plume from the mining operation 30 kilometers away, has entered the water column and is now mixing with the biological material drifting down from above. It is not catastrophic. Not yet. It is a data point. But data points have a way of becoming trend lines. On day 26, the colony of chemosynthetic organisms your predecessors discovered at 9,533 meters, the deepest living ecosystem ever recorded, discovered just months ago, begins to show anomalous readings on your remote sensors. The methane seepage that sustains them has changed. The flow rate has increased, subtly, measurably, but unmistakably. The seafloor sediment above their habitat is releasing more methane than it was 3 weeks ago. You run the analysis 3 times. The result is the same each time. The drilling operation 30 kilometers away has altered the pressure balance in the sediment layer. The methane hydrate in the sediment is responding. Micro-destabilization. Too small to trigger any alarm in the mining operations instruments. Too small to appear in any model that wasn't specifically designed to look for it. But your instruments were specifically designed to look for it. You write your first report and transmit it to the surface. You wait for a response. None comes. Day 31. The methane seepage rate has doubled since your first measurement. You are no longer looking at micro-destabilization. You are looking at the beginning of a cascade, a self-reinforcing process in which methane release warms the surrounding sediment slightly, which destabilizes more hydrate, which releases more methane, which warms the sediment further. The same feedback loop that drove Venus's ocean into the atmosphere. The same arithmetic, the same compounding, the same indifferent mathematics. At the scale currently measured, the release is manageable. The ocean will absorb most of it before it reaches the surface. The atmospheric impact will be negligible, but the trend line has a direction. And you have seen in the geological record of another planet, what trend lines with this direction eventually produce. Outside your window, the turbidity plume from the mining operation has reached your location. The water is no longer the absolute black you have lived in for 31 days. It is a murky, silt-laden gray, marine snow mixed with mineral sediment, mixed with the disturbed chemistry of 10,000 years of stable seafloor. The pale amphipods that scuttled past your window every day are gone. The silt has buried their food source. The ecosystem within visual range of your habitat, the specific, irreplaceable, never fully cataloged collection of organisms that spent millions of years adapting to these exact conditions, is being smothered under a centimeter of displaced sediment. A centimeter, the difference between existence and extinction for organisms that evolved in a world where nothing changes. You write your second report. You attach your data. You transmit it to the surface, to your organization, to the monitoring body of the International Seabed Authority, to every email address in your contact list that might have the authority to do something. You wait. On day 33, the mining operation expands its drilling radius by 15 kilometers. The new drill sites are 15 kilometers from your habitat. Let me tell you what the models show. Not the worst case, the median case, the middle of the probability distribution, given what your sensors are currently reading and the trajectory of the Cascade. If the methane hydrate destabilization in this region continues at its current rate of acceleration, the seafloor of the Western Mariana Basin will reach a tipping point, a point at which the release becomes self-sustaining without further mechanical disturbance in approximately 40 to 80 years. At that point, the release rate will exceed the ocean's capacity to absorb it. Methane will begin entering the atmosphere. Methane, 80 times more potent as a greenhouse gas than CO2. The climate models that scientists use to project the future of Earth's atmosphere were not built to account for this. They assume the seafloor hydrates remain stable. They assume the deep ocean continues to act as a carbon sink rather than a carbon source. They assume the Mariana Trench remains what it has always been, the most stable, most isolated, most unchanging environment on the planet. They assumed no one would drill into it. If the methane enters the atmosphere at the rate the Cascade models project, the global temperature increase that results, on top of existing climate change from fossil fuel emissions, would be measurable within decades, significant within a century. Venus took 2 billion years to lose its ocean to a greenhouse effect. We would be adding a new accelerant to a process that is already running. The math does not predict the end of the world. It predicts something more precise and more frightening, the acceleration of a process that is already underway by a factor that our existing planning did not account for, triggered by a decision made 11,000 meters below the surface of the ocean in the name of economic development. The same story that Venus told in its rock, told again, faster this time. On day 40, you begin your ascent, not because the mission is over, because your habitat's power reserves cannot sustain another week at this depth, and the surface support vessel is repositioning to retrieve you before the incoming weather system makes recovery impossible. You leave the sensors running. They will continue transmitting data until the power fails. Someone will read the data. Someone will publish it. Someone will cite it in a paper that 12 other scientists will read. Whether that is enough? Whether the chain from sensor to paper to policy to action is short enough and fast enough to matter is not a question you can answer from 8,200 meters below the surface. As you ascend through the water column, you pass back through the turbidity plume, through the murky gray zone where the ancient marine snow has been contaminated with mineral sediment, through the midnight zone where the last photons of sunlight surrender to the weight of the water, through the twilight zone where the light returns in the blue-gray quality that means the surface is above you. You break the surface in the middle of the Pacific Ocean. The sun is rising, the sky is blue, The ocean around you is the same blue it was when you descended 40 days ago. Nothing on the surface shows what is happening below it. The Pacific looks exactly as it always has, vast, ancient, indifferent. But you know what is beneath it. And you know what happened to the last planet in this solar system that ignored what was happening beneath its surface. Venus did not choose its fate. Its volcanoes were geological. Its tipping point was natural. There was no species on Venus to read the warning, to understand the trend line, to stop the cascade before it became irreversible. On this planet, there is. The question is not whether we have the intelligence to understand what the methane sensors are reading. The question is whether we have the wisdom to act on what we understand before the trend line reaches the point where acting on it no longer changes the outcome. The sun rises over the Pacific. The blue sky holds. For now, what if China accidentally triggers the methane bomb under the Mariana Trench? The science says it is possible. The data says it is beginning. The math says we have time. But the math also said Venus had time. What should we explore next in the deep? Should we descend into the hydrothermal vents of the Mid-Atlantic Ridge, where water reaches 400 degrees Celsius and life exists in conditions that should be impossible? Or should we witness the slow death of the Great Barrier Reef, the largest living structure on Earth, disappearing in real time, 1 degree at a time? Vote in the comments below and subscribe to HADAL before the water changes.